Okay, welcome. So today we're going to be talking about the empirical process in singular learning theory and in the Grey Book. Um, so what is this empirical process in singular learning theory? Um, let's just start by kind of orienting ourselves, like what is it? Why do we care about it? And then we'll get into some more precise definitions. So the empirical process, which we'll denote throughout by psi n, uh, basically controls the difference between the true and the empirical KL divergence of a model. So if we remember, we've got the Karlbeck-Leibler divergence can be written as this expectation of this function f. Um, and the empirical version of this is the empirical average of this. And then we define the empirical process like so. The details of this expression aren't super important for what I'm going to present. The point being is that it controls it sort of hides away the randomness of. Whoop, can you still see my screen?
Yes.
Um, uh, it is the thing that it's the random thing we need to deal with in order to apply resolution of singularities to and do the usual asymptotic expansions of the KL divergence. Um, uh, okay, whoops, forgot to put that up. Um, okay, so that's how we define our empirical process. Um, At times in the Grey Book, we also consider an empirical process, usually denoted by psi, on the resolution as well. Um, and proofs of things like the free energy formula basically require establishing some kind of convergence of random functions of psi n to some object psi, and the same for the empirical process on the resolution. Um, okay, so the goal for this talk, um, we're going to be mainly concerned with understanding convergences of sequences of random functions, such as psi uh, and the version on the resolution. And this is basically the main focus of chapter five of the Grey Book. We're not really going to get into how these objects are then used to prove the free energy formula or anything like that. And actually, what we're doing is significantly more general than how it appears in the context of the KL divergence in the later chapters of the Grey Book. My main sort of motivation for giving this talk is to clarify some really confusing aspects of this chapter, and sort of some, I guess, suggestions of proof that are, I think, a little bit take you down the wrong path, I guess. So hopefully this is gonna help with that. I'll just say throughout, because I noticed when I was looking through my slides, I didn't always say this, but throughout we're going to be thinking about real valued functions on compact spaces. And whenever we're talking about the topology of a set of functions, we're always going to be talking about the supremum norm topology. Um, uh, cool. So the setup we're actually going to be considering is a continuous function f from Rn from a pair Rn cross W to the real numbers, where W is a compact subset of Rd. Um, Now this N space is going to be where our data lives, I suppose, or that's how we should be thinking about this in the context of singular learning theory. And we're going to fix a probability distribution on Rn, and then an IID sequence of random variables distributed according to Q. Um, and then the thing we're going to be studying is this sequence of random functions, psi n, defined like so. So taking the sort of average and subtracting off the mean in each sense. Um, and our goal is to prove that in some suitable sense that we obtain a convergence of these psi n to some random function psi as n goes to infinity, where this random function we're converging to is in some way continuous. Um, cool. Any questions about the sort of general setup of this talk before we keep going?
Yes. So you mentioned that there's sometimes the empirical process on the resolution, but
Mhm.
this is like the empirical process away from the singularities or the one you would use for regular models.
Yep.
So are you sort of dismissed or like conflated these roughly like um, is that because the techniques when it comes to empirical processes are kind of the same? Like once you do the resolution, the important thing is the same for this empirical process or the more complex resolution one?
Yeah, yeah. So basically everything we're going to be saying here is applies to both. I guess there's
Cool.
one little bit of um and to be fair, to be fair, this isn't really elaborated on that much in the Grey Book either. Where when you're talking about the process on the resolution, that takes, well, that's a function on a manifold, on a compact manifold. So you need to sort of like think about each coordinate chart. But you could
Hmm.
replace this by off the top of my head, I can't really think if that like needs you to think very hard or not. But you could think about this as being psi of u, and here u is a coordinate chart of your manifold, and since the manifold is compact, the closure of that chart is compact, and everything is all fine. So the stuff we're talking about here applies to both, but we'll stick with the notation of chapter 5 and denote it by psi and by W.
Fantastic.
Yeah.
Thanks.
Cool. Any other questions? Great. Let's just talk a little bit about some background for convergence of random functions. So, um, this part of the talk is more supposed to be kind of like a lay of the land of how stuff gets proved in this area, because the arguments in chapter 5 are like ultimately kind of a standard argument. But more to the point, I'm not really expecting you to like take in, the very precise details of this, and I'm also not going to give you enough information to you know understand things in full precision. Um, Okay, so we're concerned with function valued random variables. And when we talk about function valued random variables, there's sort of two measurable spaces that we're really concerned with. If you don't know what a measurable space is, um, don't worry. It's a place where random variables live. Um, Okay, so one thing we might consider is the set of all functions from, say, W to R, which we'll denote by R superscript W, equipped with this thing called the cylindrical sigma algebra. If you're interested, it is the smaller sigma algebra such that all projections to finite products are measurable. Um, but really, what it's useful to understand about this thing is that, in some sense, it's coarse. So, by this, I mean that it is, in some ways, easy to find distributions on this product, on this space of all functions. But on the other hand, the cylindrical sigma algebra doesn't specify many interesting properties. Um, on the other hand, you might also be interested in the set of all continuous functions. Here, I'm intending W to be compact with the supremum norm topology, uh, and then thinking about the Borel sigma algebra on that. Here, the Borel sigma algebra is the set of all, is the small sigma algebra containing all the open sets of C. Um, and the main reason we care about something like this is that it's in some ways compatible with the topology that we have on C. Um, Now, there's sort of two important theorems going on this area. So we have Kolmogorov's extension theorem, which so this is not a statement of Kolmogorov's extension theorem. This is like how you might use Kolmogorov's extension theorem. Um, it it says that if you've got probability measures on every finite product or every finite product, then you can use that to prove that there exists a measure on the set of all functions from W to R, such that the push forwards agree. In practice, what this looks like is if you want to construct a random function psi, then you define your intended joint distribution for all possible finite subsets of W. Um, and then you apply, assuming you satisfy the conditions of the theorem, which I haven't actually told you, then Kolmogorov gives you a random variable on the cylindrical space with the specified finite projections. This is discussed a little bit in the Grey Book in remark 5.6. Um, the main reason I'm talking about Kolmogorov's extension theorem is to contrast it with Prohorov's theorem, which goes via a different route. So Prohorov's theorem lets you take a sequence of probability measures on the space of continuous functions, and it can be used provided you can show that the conditions are satisfied, um, that you get some convergence in distribution to another probability measure on the set of all continuous functions. So what this looks like in practice is if you want to construct some random function, some continuous random function, you define continuous random functions psi n, so it's like approximations of your desired random function, and then you show the sequence converges using Prohorov's theorem. The reason I'm sort of drawing this distinction, by the way, if you're someone that has not read through chapter 5 of the Grey Book, is there's times when it seems a little bit confused about which kind of route is being taken here. So I'm aiming to kind of draw a clear distinction between these two approaches. And yeah. Um, Before we move on and talk about the main focus of this talk, I want to talk a little bit about how Brownian motion is constructed, because really the argument given in chapter 5 is in some ways related to one of these two constructions of Brownian motion. Um, so for Brownian motion, what we want to do is we want to define a continuous random function from the half line, which we think of as being time, to R or to Rn if we care about constructing Brownian motion on Rn. We want it to have some property. It needs to have independent normal increments. This isn't particularly important. Um, and there's two distinct approaches, at least two sort of approaches to constructing Brownian motion with quite a different flavor. So there's an approach that goes via Kolmogorov's extension theorem. Um, this proceeds as follows. So you start by defining the finite dimensional distributions on each finite product, and then you use Kolmogorov's extension theorem to obtain a distribution on the product sigma algebra. And then you think, oh, well, I did want it to be continuous though, and if I've just got some random, if I've just got some function on Rn, sorry, on R to the set of all functions from the half line to R, maybe I can show that the probability assigned to the set of continuous functions within this space is equal to 1. Um, uh, but this doesn't work because the set of all continuous functions isn't actually measurable with respect to the cylindrical sigma algebra. So in fact, this approach needs to proceed via a different method where you take a random variable distributed according to the distribution you obtain, and then you have this sort of argument where you modify the random variable such that the distribution doesn't change, and you end up with something that is almost surely continuous. The other approach, and this is the approach that sort of I think is the right way to understand chapter 5 of the Grey Book, is an approach via Prohorov's theorem. So Prohorov's theorem is about only works on functions defined on compact parameter spaces. So you start out by defining continuous and finite time approximations to Brownian motion. And then you use Prohorov's theorem to obtain finite time continuous Brownian motion, and then on this space of continuous functions. And then you glue these copies into a process with continuous sample paths. Okay. And really, the approach you take in the Grey Book in Chapter 5 should basically be understood as being very similar to the sort of first step of this diagram, where you define where you look at the convergence of where you start out with continuous sort of approximations of the thing you want to think about, and then you show that it converges entirely within that space. And the sort of references to Kolmogorov's extension theorem and the cylindrical sigma algebra in the Grey Book are not really relevant to the sort of main argument that is going on here. Okay, let's move on to sort of talking about this convergence proof. But before I do that, do we have any questions about that? Cool. Okay, so just as a reminder, let's go through the objects and notation that we wanted to talk about. So we're going to be thinking about a compact subset of RD and a continuous function f from this pair of spaces here. We're thinking about the set of all continuous functions from W to R with the Borel sigma algebra. We have a probability distribution on RD and a set of IRD random variables distributed according to Q. And then what we're interested in studying is this sequence of C-valued random variables, psi n, defined as follows. And our goal is to prove that these psi n converge in distribution within this measurable space for some continuous function valued random variable psi. Okay, so let's talk a little bit more about Prohorov's theorem. So let capital psi n denote a sequence of probability measures on this measurable space. And we say that this sequence of probability measures is tight if for every epsilon there exists a compact subset of functions C, a compact subset of C, such that the probability assigned to that subset is greater than 1 minus epsilon for every element of our sequence. And we can apply this same definition to a sequence of C-valued random variables. We say that the random variables are tight if the corresponding distributions, which as a reminder are defined like so, if these are tight. Prohorov's theorem is as follows. So as long as the domain of our functions are compact and the sequence of random variables are tight, then psi n converges in distribution to some continuous function valued random variable if and only if every finite projection of these random variables converges in distribution. I'll just point out that really this is a corollary of Prohorov's theorem, which is about relating tightness to a quantity called relative compactness. Any questions about this or what we've talked about so far?
Oh, I have a question.
Yep.
Can you hear me? So is the goal to like prove that the convergence is over like functions that are like small valued? So are like difference between training loss and like generalization error is small?
Yes. So I guess so in terms of how this fits into singular learning theory, I guess that's not something we're really covering in detail in this talk. but it's an ingredient of what goes into proving something like the free energy formula. Um, and
Mhm.
basically, uh, so yeah, it's about it's to do with the difference between, I guess, like the empirical loss on a data set and the sort of expected loss on a data set. So you can think about Kn of W being the empirical loss at a parameter and K of W being the expected loss at a parameter. And um, in singular learning theory, like we or in order to, so the geometry of K of W is of the expected loss is important. But in order to start sort of talking about this geometry, we need to do something with the kind of stochasticness that arises from the empirical loss. And the way that this is dealt with is by rewriting the empirical loss like this, and then studying this thing here, this psi n of W random function. Does that answer your question?
So I guess are we expecting psi n to like in the limit of very large n to be like zero, like the zero function or something like that?
So it'll converge to a uh, yeah, not quite. So it will converge. So it's a random variable. So it will converge to a random variable, right? But the sort of finite dimensional projections of this random variable. I'll state the theorem at the end. Will have mean zero, and there'll be an expression for the variance as well. So they're the quantities that we um, that sort of come up. I mean, so it's yeah, it sort of, I guess the important parts of this is that like I'm pretty sure. So it's important that this psi n converge to a function that is at least almost surely continuous, right? So you might imagine that you've got this sequence of functions that converges to a function that is not continuous, and that might cause problems for what we're hoping to do with this. Um, and then we also care about like controlling the statistics of that random function, which we'll also get to a little bit later. Any other questions?
I also have a question.
Mhm.
I worked through the sketch of this section at the start of the book, section 1.4.1, I think it is. Um, and it's been a lot of time kind of defining the empirical processes and not a lot of time discussing the proof of their convergence. And uh, I think there's like two kinds of convergence of random empirical processes like this or something. And I'm wondering if you could just help me clarify this. Um, so if you just wanted to know that your sequence of random function valued random variables converges uh, in the first sense, which I've heard called like weak convergence, then you just have to check if each of the finite um, projections converges in distribution.
Mhm.
But you don't need this tightness assumption. And then if you've, and that is like, uh, I think much more straightforward, and you don't need a theorem for it, like a named theorem like this. But here we're doing something like we have this additional tightness assumption, and then we get a much stronger guarantee on the nature of the convergence in distribution. Is that right?
Yeah, that's like maybe 80% correct.
Okay.
So I found this section really confusing, which is kind of like, what started me going down this path of thinking about this. Um, so I want to bring up, okay. So the first method that gets talked about in that book is actually this method via Kolmogorov's extension theorem. So
Okay.
yeah, okay. Before we talk about that, let me say so the difference isn't so much about weak convergence versus some other some other form of convergence which isn't convergence in distribution. In all cases, we're talking about convergence in distribution. But the I guess the space in which that convergence is happening is different, right? So in the case
Okay.
sketched in the very start, it's the exact same argument going via Kolmogorov's extension theorem, where uh, you you I guess rather than defining the intended joint distributions, you show that uh, the sort of the joint distributions at every n converge in distribution, right? And then that gives you, I guess, your like intended joint distributions. And
Hmm.
then Kolmogorov says, okay, well, because all of these are compatible, um, then that gives you a distribution on the set of all functions, which is like, such that everything makes sense, right? Like such that you get agreement on your joint
Hmm.
distributions. Um, so that is establishes a kind of convergence in distribution, but it happens within this sigma algebra, um, this cylindrical sigma algebra, which is really coarse, and it doesn't let you ask a question like, did the function I converge to, is that a continuous function? Right? Like it's happening in a place where you can't ask the kind of questions about like sample paths or something like that, that you need. Or by sample paths I mean, I guess, like an outcome of your random function, like a particular random function. um, uh, you can't like use the distribution you get on this space to address questions around like continuity and things like that. So instead, we need to go via a route where we prove convergence directly, like within the space of continuous functions, using a stronger, like a more a finer sigma algebra. And that means we can't use Kolmogorov's extension theorem anymore. Um, does that kind of
Yes.
Yeah.
Thank you.
But yeah, I agree this is quite confusing. Like as in the book is quite confusing in this way. Cool. Any other questions? Okay. So we just mentioned Prohorov's theorem, um, and this definition of tightness. Um, so basically, the too long didn't read of that slide is it suffices to show that our sequence of random variables is tight. Um, okay, so let's think about how we might do that. Well, a component of tightness is dealing with a compact subset of C, our set of all continuous functions from W to R. Um, how do we show that sets here are compact? Now, this is like harder than it maybe sounds, because things like closed balls are not compact in this space. Um, Luckily, we have a big theorem for this. So if we've got a compact set of RD and we think about a subset of the set of continuous functions on W, um, then the closure of that subset is compact if and only if it satisfies both of these conditions. One is that F has this uniformly bounded property, which means that there exists an M such that the supremum over all inputs is less than M for all functions in that set. Um, this supremum, there should be an absolute value sign around the F here. Um, I hope you can see my mouse where I'm indicating. Um, and then the second property, it must
I
satisfy.
don't think we can.
You don't think so?
Can you indicate again? I might have missed it.
Uh,
No, neither can I.
Yeah, can't see the mouse.
okay, I can't seem to. Oh,
Oh, now
oh
now I
yeah,
can.
absolute values here.
Oh,
Yep.
yeah, cool.
Um, The second condition we need to think about is uh, a condition referred to as being equicontinuous, which says that for every epsilon, there's a distance between inputs, such that for every pair of, for every function f in our set, that the difference between the outputs is less than epsilon, so long as the distance between the inputs um, is less than delta. Um, Now, only uniform boundedness is discussed in the Grey Book's convergence proof. Um,
Wait, could you clarify that point?
I'll have a little bit more to say about it later, but uh, basically, um, when the in the proof of theorem 5.9, which is the theorem that states the convergence result, when when the tightness part is being proved, it sort of only establishes the uniform bounded condition on the compact set in question, rather than the equicontinuous. Um, the equicontinuous. I think this might be a bit clearer once I've sort of sketched out the components, how each of these things is proved, and I can sort of point out what results are missing from the text.
Okay, but importantly, it's just something that is not explicitly proved.
Yeah, yeah,
It's just
yeah.
missing.
It's
Okay,
not it's
cool.
not missing. It's not proved, and it's also not like mentioned. There's no discussion of like
Yeah.
the uh, yeah, like it's sort of there's no discussion of the need to prove equicontinuity, or that proving compactness in C is a little bit more complicated than in a finite dimensional Banach space.
Oh, I see. Okay, yeah, sure.
Um,
Oh, right. So is this okay. Well, yeah, you can point that out later.
yep.
Thanks.
Um, I'm gonna try and get rid of these. Cool. Okay, now I need to like just state a condition, which is a little bit cumbersome. Um, we actually don't really need the details of this condition anywhere in our discussion because I'm sort of sketching the thing, and we're actually not going to prove any of the like detailed lemmas that use the details of this condition. The sort of wouldn't be complete. The talk wouldn't be complete if I somehow didn't say this. Um, so for numbers s greater than 1, we consider the Banach space of functions on R n to the R. So here now we're talking about functions on our data space, if you like. And this is, there's also a missing S in here. Um, uh, and then we say that our function f is LSQ valued real analytic if for every point in parameter space, there are coefficient functions living in this Banach space, which are indexed by d tuples of integers, such that this is true for all w in some local neighborhood, sorry, some open neighborhood of w star. So this is very similar to the definition of an analytic function, except that now we have another input to our function f, and we're requiring our coefficients to be sort of sufficiently nice integrable functions of that other input. Um, Here, I'll also say that the right-hand side here uh, is required to converge absolutely um, in uh, is required to converge absolutely in the Banach space LSQ for all W, which means that this quantity here is finite. I notice someone has corrected my formula, which thank you very much for doing that. Um, uh, yeah, I kind of don't want to linger too much on this definition because we actually don't. need to deal with it that much. But this is the property that F needs to satisfy for all of these results to go through. Cool. Can I change slides? There we go. Okay, so you can sort of break down the components of this proof for convergence into sort of two main lemmas. A lemma that is used to establish, I guess, the uniform boundedness part of the compactness theorem, and a lemma that is used to establish the equicontinuous part of the uniform boundedness theorem. Um, so this lemma is in the grey book as theorem 5.8. And it says that so long as W is compact and F is this LSQ valued real analytic function, then this supremum is finite. um, Given this lemma, we can recall Markov's inequality, um, which says this. And then what that means is that we have the probability of this probability, it can be bounded above like this. The upshot of all of this is that for any epsilon, there exists an M such that this condition is true. So this is a key component of proving the uniform boundedness. The other component of this is a similar lemma for equicontinuity. So this is, I guess, the thing that is not in the grey book. So with the same conditions on W and F, there you can show that there exists some delta max and B such that for every delta in in this interval, you get this bound in terms of delta. I'll just point out as well, we don't really use this lemma, but it's used in the proof of this lemma. You need to establish here that the partial derivatives of f of an LSQ valued real analytic function are themselves LSQ valued real analytic. Using a similar Markov inequality argument as before, this implies the following condition, that for any epsilon and eta greater than 0, you can find some delta so as to bound this probability. Okay.
So, where is this proven, if not in the grey book?
In my notes.
Got it.
Yeah, yeah. But I also want to say, like, if someone knows of a place where this is dealt with in singular learning theory, other than the grey book, I'd be good to know about that. I can't find it in the green book, and I'm not really sure where else to look.
I mean, I guess there are all of the papers,
Yeah, yeah.
but
I think
um,
I haven't been able to find it. I'm not sure I have like
hmm,
the best knowledge of all the like sort of pre-grey book literature. But yeah, I haven't talked to anyone that has like known a better place to look for this sort of
hmm,
proof. Um,
hmm,
I will say that this, yeah, it's like it's not like the argument that proves this lemma is like radically different to the argument that proves this lemma. Like it requires a little bit more. So like this this stuff to do with the derivatives is important. Um, but like kind of, you use similar ingredients to prove this one. Um, uh, yeah, was there anything else I wanted to say on that? I guess that yeah, yeah. I guess that's all I want to say on that.
but
Um,
yeah,
it is not in the gray book, I don't think like the papers will have it. The papers are generally less detailed, I think. Like the gray book,
Yeah.
like the papers spell out the gray books, the fact that the empirical process is even discussed at all,
Mm.
um, in is sort of like it's these are treated as sort of background knowledge,
Mhm.
um, and this could be just something that is missed, or just treated as too elementary or something like that.
Mm.
But I think you're right that because there is something new here, which is this LSQ, uh, the the argument sort of factors through this complex analytic, um, real analytic property that it should be sort of mentioned. But
Mhm.
I think if I were to guess, is something like this is such a strong condition, then generally what people needed to prove to prove that empirical process converge, that like it's like, guys, this is an empirical process, and you have a very strong condition. Yeah.
Mhm.
uh, yeah.
Cool. Um, okay, so just to remind you, or based on these lemmas, you can establish this inequality here, and this inequality here. And now tightness, like this is now in living in the world of a very standard argument, having established those two inequalities. I guess I'll quickly flick through this, but um, I guess yeah. Anyway, so let some epsilon be given, and then we are going to define an M uh, such that for this set of continuous functions f prime, we have that the probability of each psi n being an f prime is greater than or equal to 1 minus epsilon on 2. And then for each integer k, we're going to let delta k be such that for each fk, we have this inequality involving the probability of psi n being in fk. We're then going to take f to be the intersection of all of these sets and k to be its closure. And k is compact by the uh, Azzarello-Ascoli theorem we mentioned before, and psi is in K with probability greater than 1 minus epsilon. And this establishes tightness. This proves tightness by definition. Um, so yeah, I think this is the kind of the right way to think about what is going on in chapter 5 of the Grey Book, is that you sort of need to establish these two inequalities, which are kind of dealing with the uniform boundedness and equicontinuity components of the Azzarello-Ascoli theorem. Um, this establishes tightness, and then the main theorem then follows from Prohorov's theorem. Um, let's state that main theorem. So theorem 5.9 in the Grey Book says that if W is compact and we have these LSQ valued real analytic condition on F, then the psi n is tight, um, and that additionally, for every finite subset of W, the vector converges to a normal distribution with mean variance and covariance as given there. This is just the usual central limit theorem. And then together, these two facts mean that psi n converges to some function psi in distribution, where psi is continuous, and every, I guess, finite projection of psi uh, has the above normal distribution. And this follows from Prohorov's theorem. Um,
Wait, question.
yep.
The last statement there, uh, Prohorov give you that the convergence is like uniform in such a way that psi is continuous, but does it also give you the normal distribution thing? I thought that part is the Kolmogorov thing.
It's not really Kolmogorov. So, like, I guess I kind of hid that. I like stated something I called Prohorov's theorem before, um, which was really like a corollary of Prohorov's theorem.
Yeah.
Um, uh, I guess this is like where that comes into it. So really, we want to talk about relatively compact sequences of distributions, um, and then you can show that, like, if these uh, like it doesn't go via Kolmogorov's theorem at all. You just need to like it's not too hard to show that, like, if you get this convergence, then you must also get convergence at the
Ah,
level
right.
of finite
Point one.
distributions, basically.
Right. Okay.
Sorry, I was
Right.
overcomplicating that by mentioning relative compactness. It's just a matter of observing that, like,
Yeah.
if you obtain convergence, then the finite dimensional distributions must also converge. Yeah. So again, Kolmogorov is not involved in the
Right.
actual
Right.
part we want to use for SLT. Yeah.
Right. I guess that is true. This is just like if you converge uniformly, you converge pointwise as well, something. Yeah.
Yeah, yeah. I mean, yeah. If you're thinking about, like, just the measures and, like, taking a set, then, like, just
Yeah.
by these look by looking at these random vectors, you're just looking at, like, the um push forward measure. So you're just evaluating the measure on, like, a pullback of some measurable set along one of the finite projection maps. So yeah. Um, okay. Any other questions about the statement of this theorem?
I didn't really follow the that discussion just now with Edmund.
Mhm.
Um, what uh, what does this is a very basic question. What does uniform convergence mean in this context?
I guess, like, uniform convergence is, I'm guessing Edmonds was sort of referring to, um, like, the uniform convergence of functions on the continuous, like, in the, like, convergence in the supremum norm topology
Yeah.
on the set of all functions from W to R. Um,
Okay.
yeah,
But we have random functions. So
yeah,
Yeah.
where would we see uniform convergence?
I think I'm just like making analogy. I'm not
yeah,
sorry.
Oh, okay.
The random part is definitely an extra component, and that is why this whole thing is more complicated. The analogy here is just that to uniformity is the thing that gets you from continuous sequence converge to continuous function. Um, that's the extra thing that you need. Here you have something very much like a uniform uh, uh, convergence sort of criterion, just in a much more complicated space. Yeah.
Okay.
but we've established convergence in the Borel sigma algebra of the where the topology is the topology that defines uniform convergence. So there is a way in which this is, like, the right way, like, that it's not, like, unreasonable to call this, like, some kind of uniform convergence. Um, if that helps.
Okay. Okay. I have one more question, which is that this is framed in the book in terms of Gaussian processes. Um, if I
Mhm.
understand on this slide, uh, this is everything we need to sort of talk about this in terms of Gaussian processes, right? So we have that psi is uh, every finite joint distribution of psi has a Gaussian distribution, and that's the defining characteristic, I think, of a Gaussian process.
Yep.
Cool.
Yep. So yeah, I think
So so
this is
uh,
psi n converges to a Gaussian process.
yeah, yeah. Prohorov's theorem is being used to show that it converges um, to something with whatever the joint distributions converge to, and the central limit theorem is being used to show that that is uh, normal distributions
Yeah.
in particular. Okay, cool.
So the form of psi, like remember, I don't want to flick back all the way, but remember it was like one
Yeah,
over n,
yeah,
f of x minus the mean of f of x. Like like the reason it looks like that is because you want to apply the central limit theorem to the
yeah,
finite dimensional distributions. Um, like the Prohorov's theorem, you could use that to prove convergence for functions that don't look like that, right? But
yeah.
um, yeah.
Yeah, I don't know if you mentioned this at the beginning. I missed a few minutes. But this part of the answer to John or some I think just now, which is that this is just a function form of central limit theorem.
Mhm.
Except you also want to establish a few property that the thing that you converge to is continuous, which is pretty important. Um, the other sort of comment on this the central limit theorem form before, which is that that the form of f is the form of psi n is precisely the normalized central limit theorem form. So in central limit theorem, you have like x minus the mean divided by the standard deviation.
Mhm.
So that you want it to converge to, and then you show that random variable converge to the standard Gaussian. Except this is not quite that, because the form of psi n is divided by something of the order of um of the order of the standard deviation. It's a constant of um
Mm.
yeah. And but that is sort of part of the key thing, because the standard deviation at the true distribution is zero, which is a problem, um, because you are dividing by zero, or that you have a Gaussian distribution with standard deviation zero,
Mhm.
which is not a Gaussian. Um,
Yeah. So this I'll flick all the way back. Uh, this is related to these things here.
yeah, the part that you still need to prove is something like that thing is the standard deviation of that thing.
I think here, can you just not like the F is just different in what we've been talking about, right? Like
What do you mean?
like you just define F to be like define like say F prime to be this F divided by root K of W.
Yeah, so sure, you can define that. I think uh the point I was making here is that uh you wouldn't get that the standard the thing this converge to is a standard Gaussian, like
Mhm, mhm, mhm. Yeah.
uh, uh, variance one Gaussian. Yeah.
Yeah. Yeah. Sorry, I realized you were writing. But yeah, so we get sorry. Yeah, so here we get the covariance is depends on the values of the this second point here, the where the covariances are different. Yeah.
Yeah.
Okay. I'll just quickly flick through how this sort of compares and fits in with what is in the grey book. So uh, just to summarize, the grey book establishes this uniform boundedness condition in theorem 5.8. But the proof of tightness doesn't really discuss equicontinuity. Um, and the discussion of the proof of the convergence theorem in theorem 5.9 sort of discusses this cylindrical sigma algebra, which I think is not really relevant to what is being trying to be talked about in that theorem. Um, and Yeah, because I guess because equicontinuity is not discussed, there's sort of not really a mention of this fact about the derivatives of f inheriting the LSQ valued real analytic property, which is sort of what you would expect, but it's sort of not obvious um, from the chapter that this is like an important component of of getting this all to go through. Um, I think that's the end of the talk. I'll just quickly mention that if you're looking to learn about the sort of Prohorov's theorem and stuff, I used this book, which is very good. Um, cool. Let's stop the recording and we can keep discussing if we want.